So this is joint work with my postdoc Aaron Potechin while we are at Cornell and the Institute for Advanced Study. And before talking about tensor completion, let me talk first about a related problem that most of you will be familiar with. So in matrix completion, there's an unknown matrix, and we observe a few of its entries, and the goal is to fill in the missing entries. And this kind of problem, comes up, for example, in recommender systems, where each user may rate just a few movies, and we would like to infer the user's ratings for all the other movies, in order to make recommendations to the users for what to watch next or so. Okay, that's a very prominent motivation for this problem. In order to get theoretical guarantees for this problem, you'll need to make some assumptions about the unknown matrix and the entries that we observe. And the standard assumptions here are that the matrix has low rank, that the matrix is incoherent, which means that its singular vectors are close to orthogonal to the coordinate basis vectors, and that the entries that we observe are distributed uniformly at random in the matrix. Now, under these assumptions, it is possible to recover the unknown matrix, and there are even efficient algorithms to do that. Okay, and the algorithms for matrix completion, they come in three flavors. And that will also be true for the problem that we will study, tensor completion. First, there are algorithms whose analysis is based on statistical learning tools, for example, Rademacher complexity. And second, there are iterative algorithms, for example, alternating minimization or non-convex gradient descent. And finally, there are algorithms that are based on convex relaxations and that are analyzed by explicitly constructing a dual certificate that certifies that the convex relaxation computes the unknown matrix exactly. And these, these flavors have different strengths and weaknesses, and it's an interesting general question to better understand what's the relationship between those three flavors. Let me at this point, remark that if you just care about having an algorithm that runs in polynomial time, then the best, the last technique based on constructing dual certificates tends to give the strongest bound, especially if you care about exact recovery. And so one representative result, actually obtained in a sequence of works that uses this explicit construction of dual certificates, shows that there is a convex relaxation, which is a simulation program that in polynomial time recovers exactly an unknown rank R matrix that is incoherent just from R times n of its entries. Okay, and this is close to the information theoretic limit in the sense that if you would observe for such a matrix much fewer than R times n entries, then it would not be uniquely determined by the observations. Not necessarily. Okay. And this work is not directly about matrix completion, but about a more general version of the problem, that is equally important but much less understood. So in tensor completion, the unknown object is not a matrix but a higher order tensor, which means that instead of having two indices like a matrix, it's an array indexed by three or more indices. And for simplicity, we will focus on order 3 tensors, which we can visualize as these kinds of cubes. But if you want, you can also apply our techniques to higher order tensors in a straightforward way. Okay, and this tensor completion, has similar motivations as matrix completion. For example, if you think about more advanced kind of recommender systems where, you make recommendations based on, user activity and location, then that will naturally be a tensor completion problem. Also in 3D images, those are naturally order 3 tensors. Also in the semantic map, order 3 tensors naturally arise where the 3 indices correspond to subject, verb, and object, and you have a one there. Entry is 1 if this relationship holds. Okay. And but there's also a greater goal here, which by studying this more general version of the problem, we hope to gain insights, in general about how to cope with missing data. And ideally, what we'd like is a systematic way to come up with the right algorithm for any particular missing data problem, as opposed to investing a lot of creativity into the process of finding a good algorithm for such a problem. Okay, and in this work, what we show is that there is an algorithm based on a particular kind of assimilation program called sum of squares that is able to efficiently recover order 3 tensors in n dimensions of rank R if the components are orthogonal by observing just from R times n to the 1.5 entries, and the recovery is exact. Okay, and what's interesting about this result is that so if you want to do exact tensor completion, then this result gives the first polynomial time algorithm that improves over the naive reduction to matrix completion, which would require you to sample n squared entries as opposed to n to the 1.5. And the way we achieve this result is by extending the techniques of constructing dual certificates to the tensor setting, and this hasn't been done before. Okay. And let me talk about previous works on tensor completion. So they talk about approximate tensor completion, where you want to get a tensor that is epsilon close to the unknown tensor. And here, there is a result Barak and Moitra. It uses exactly the same simulation program as we are using, but it analyzes it not by constructing dual certificates, but by statistical learning tools. And what they show is that in this way, they show that you can get an epsilon closed tensor from, if you take 1 over epsilon squared times more samples than we would need for exact recovery. And there's also works that use these iterative algorithms, in particular alternate minimization, due to Jane and O. And what they show is that you can get an epsilon closed tensor by investing something that is logarithmic in the desired accuracy, more samples, but also the dependency on the rank is not quite right. Okay. Now, one very interesting aspect about tensor completion is that there is a big gap between the information theoretic bounds. So those, so they say that you can recover this kind of a tensor in exponential time if you just get R times n entries, and the efficient bounds, which require n to the 1.5 entries. And the conjecture is that this gap is inherent. There's also some evidence for that in forms of sum of squares lower bound. And it's a very interesting future direction to strengthen these kinds of lower bounds to really get more confidence in this gap between information and computational bounds are inherent. Okay, so now let me tell you about techniques. And instead of walking you through the algorithm, let me. Okay, I think I forgot to reload this thing, which is might be bad. Maybe let me do that now. Okay, nothing broke so far. Okay, sorry about that. So instead of walking you through the algorithm and its analysis, let me try to explain where the algorithm is coming from and what are the general concepts behind it. Okay, so let's make the setup more concrete. So we have an unknown tensor x, that is our ground truth, and we know some properties about it, and this is captured by this set script x sub r. So this is our hypothesis class, and for example, we know that the tensor has low rank, and but for now it's not so important what those particular properties are. And now there's a set of entries omega that we observe in the tensor, and our goal is to recover the original tensor x just from its entries in omega. Okay, now we can ask two important questions here. One is, do we have enough information? Does x restricted to the entries in omega uniquely identify the whole tensor x? So this property is called identifiability. And the other question is, can we do this efficiently? Given x restricted to the entries in omega, can we efficiently compute the tensor x? And clearly, identifiability is necessary for efficient recovery. But we could ask, is it also sufficient? Okay, and of course, the answer to this question should be no, because you can imagine situations where the ground truth x is identifiable, but the task of computing x requires exponential time. Okay, but however, that's the easy and not so interesting answer. So the real answer to the question is okay. So I'm not sure if I said the right thing. So the answer should be no. It's not sufficient. I think okay, whatever. And but the real answer is that it's yes. Okay, it should be sufficient. And if you make the following condition, which is that the proof of identifiability, okay, so the way you prove that this holds, and that should be captured by a restricted but powerful proof system called sum of squares. And if that holds, then indeed if your proof of identifiability has this property, then indeed you can get efficient recovery. Okay, so that's one thing. However, even this question is not interesting by itself, because actually it's just rephrasing something that we have known for a long time. What is it rephrasing? So if you have a recovery algorithm that is based on convex relaxations, and you analyze it by constructing dual certificates, then this dual certificate, you can always view it as a proof of identifiability in some restricted proof system that corresponds to the convex relaxation. Okay? But what is interesting about this claim is that so this gives a new perspective on how to use convex relaxations for recovering missing data. And in this new perspective, you don't have to think about the concrete convex relaxation you're going to use, but instead you can just think about these proofs of identifiability. And this new perspective turns out to be useful for tensor completion, and it could be useful for many other problems as well. So now let me make this more concrete. So suppose that our hypothesis consists of all tensors that are sums of R rank 1 tensors where the corresponding vectors are orthonormal. And now we can look at, we have the set omega of observations. Now we can look at all tensors that agree, that have the same entries as the ones that we observed. Okay, that are consistent with our observations. And now what does this set of vectors is a very crazy set. This set of tensors, low rank tensors, is a very crazy set. Highly non-convex, some algebraic variety. And what we know is that our ground truth tensor is somewhere in there. And now identifiability just means that if you look at these vectors that are consistent with our observations, that that intersects our hypothesis uniquely. That what it means that x sub omega uniquely identifies our target tensor x. Okay. But a priori that doesn't mean that we can recover it efficiently. So instead we look at a convex relaxation. And so we could look at the convex hull of these low rank of these kinds of low rank tensors. And now we could ask, is it still true that the intersection between this convex hull and the things that are consistent with our observations is that unique? Okay. So now that's clearly less likely thing, but here it happens to be the case that the intersection even with the convex hull is unique. And now notice that if you have two convex sets, so this set is convex and this set is convex, and they intersect uniquely, what it means is that they intersect in this tangentially, and this property you can characterize for convex sets, you can characterize in terms of the normal cones of the convex sets at this point x. Okay. In particular, what we want is that there's a shared vector in the normal cones, and that is equivalent to constructing dual certificates. Okay, so that is the viewpoint for how to use convex relaxations to do this recovery. Now, there are two challenges in this context. One is, we somehow have to show that this common normal vector exists in these normal cones, and here what we're going to use is a construction due to Cross and Reich that has been used for matrix completion that uses alternating projections. I will say a little bit more about it later. But the main challenge, and which is a crucial difference to matrix completion, is that this actually doesn't really make sense for tensor completion. The reason is that this set here, even though it's convex, it's NP hard to optimize over. So it's intractable to compute the intersection of this convex set and this convex set. Unlike for matrix completion, where this is a tractable problem, where you can compute the intersection of the analogous sets efficiently using this nuclear norm minimization. And so how do we resolve that? So what we do is, instead of looking at the convex hull of the set, we will look at the appropriate sum of squares relaxation of that set. Okay, so that's the plan. Now, one crucial thing that we will do is that, a priori, so this could mean that we have to, it is going to be really painful, because now we have to understand, the normal cones, not of this set, which is a somewhat simple set, but of the corresponding sum of squares relaxation. Okay, so that sounds like it would be very painful. And so what we do, so instead what we do is we do something else. We pretend that we could actually work with this inefficient convex relaxation, and then we realize that this kind of question, this normal cone question, is a question about polynomials. Okay, and now what we'll do is we will resolve this question about polynomials in the sum of squares proof system. So this is a proof system about polynomial inequalities. And if we are able to do this, if you're able to sort of resolve this question about polynomials using the sum of squares proof system, that turns out to immediately imply that the sum of squares relaxation, does the correct recovery. Okay, so let me tell you a little bit about that. So if you sort of look at what this characterization in terms of normal cone means, what you will get is that this convex hull of the low-rank tensors touches the set of tensors consistent with our observations, if and only if there exists a polynomial that is a linear combination of these polynomials corresponding to our observations, and the polynomial should have the property that its unique global maximizers over the unit sphere are exactly the components of the tensor X. Okay, so that's what the inefficient convex relaxation requires us to show, this kind of a polynomial. Now the issue with that, and now you see why these things are NP hard, is maximizing degree 3 polynomials over the unit sphere, unlike for degree 2 polynomials, that's NP hard. And so what we do instead, we will certify this property using sum of squares proofs. And essentially what it boils down to is, what you have to show is that if you somehow are able to construct this polynomial t, what you have to show is that the polynomial, and suppose that the polynomial has value 1 at the points a1 up to ar, what you have to show is that the polynomial 1 minus t of y, that should be a sum of squares over the unit sphere. Okay? And a priori, this might be, a reformulation, to an equally hard problem. But the nice thing about it is that, there's a growing general toolkit for showing these kinds of statements, for showing that something is a sum of squares over the unit sphere. And we have a website with lecture notes on these kinds of things. Thanks. Okay, and if we are able to do this, if we are able to show that such a polynomial exists, where this property star is certified by a sum of squares proof, that turns out to imply that the algorithm that we proposed, using the sum of squares relaxation of the convex hull, that does the recovery efficiently. Okay, so now let me just, so that's all I wanted to say about in terms of sum of squares proofs. Okay, so nice things about, we can use a lot of technology that has been developed about sum of squares proofs. Let me talk a little bit about, how to construct this polynomial t of y, and for that we can completely, forget about sum of squares. So just think about constructing some polynomial, and here we'll use this idea of alternating Euclidean projections due to Gross and Recht. So if we start with this kind of polynomial, so that will satisfy the second point, then what the first thing is that we'll do, we project into the span of those polynomials so that we satisfy this condition. But now we will violate, potentially this condition. And now what we do in the next step is, so projecting to this set is very hard. So what we do instead, we project to an affine linear space that contains that is a superset of the polynomials with this property. And what we do is we look at all polynomials that have where the value at the points a1 up to ar is 1, and where these are supposed to be global maximizers. So what we do is we require the gradient to vanish there. That's a necessary condition, and that's some affine space of polynomials. And now what we do is we project into this defined space of polynomials, and now we alternate between projecting to this space and this space. And what you can show is that this converges, and it converges to a polynomial that satisfies this property, even in the sum of squares sense. Okay? So let me conclude. So here's our recipe for getting efficient algorithms for recovering missing data. So first, prove identifiability, then check that the proof steps are captured by sum of squares, and then you can enjoy your efficient recovery algorithm. Some open questions. It would be nice to have a truly general characterization of when efficient recovery is possible for these missing data problems. Another question that I like is, I really would like to get a better understanding of this alternating projection business. Maybe get a different proof of that. That would be very nice. Thank you very much.